and on behalf of the physics department, I welcome Professor Patrick Das Gupta for today's talk. And Professor Patrick Das Gupta is known to us, and it's a very familiar face to us. And I think you might have visited many times to Pilani campus
Oh,
for different
yes,
talks.
yes. I
So
mean, Topomai himself had invited me after Stephen Hawking had passed away, and
okay,
we had a lecture tribute.
okay.
And before that, I visited twice to give talks when Subhash Karbelkar was in the department.
Okay.
Yeah.
Yeah. Okay. Okay. So formally, I welcome Professor Patrick Das Gupta, and let me talk about the department right now. So right now we have 21 faculty members in the Pilani campus, and out of 21, one faculty is working in the off-campus mode, while 20 faculty members are working in the on-campus mode. And the research profiles in the department, it ranges from the very basic to particle and nuclear physics and cosmology, and then condensed matter physics, atomic molecular physics, and the complex system and statistical mechanics and biophysics, and also very strong experimental condensed matter group we have. And right now we have around 35 PhD students who are working in the on-campus mode. And we have a large number of individual level of sponsored fundings. And currently the department is supported by DST FIST. And that's all about the department. So I don't want to be an eclipsing object between you and the audience. So I now invite Professor Patrick to take over the floor.
Thank you very much, Professor Chobisa. What I will do is I will now switch off the video and go to the sharing of slides.
Yeah, it's okay. No problem.
Yeah. So are the slides visible? Now I'll go there and go into the full screen mode.
It's not visible till now. We should wait because it takes some time.
I don't know why I'm not able to share the screen. When I'm clicking on share, nothing is happening.
Did you click on the present now button?
Sorry?
Present now
button.
button
Called present now.
Yeah, I did so. But
there are three different options.
yeah,
You are in
entire screen, a window and tab. So I clicked on entire screen.
Okay.
When I do that, and then try to click on the share, nothing happens.
No, so okay, so I'm not sure if did you click on you need to click on the window first. You know, it will show you in that black box, it will show you some window. You click there first and then click on share.
Okay, great. Yeah. Now I understand. Yeah. All right. All right. Great.
Yeah, it's coming now.
Yeah.
Now it has come, yeah.
Very good. Very good. Okay. I will now go into the full slide mode. So now the slides are visible, right?
Yes.
Yes.
Yeah, great. Okay, uh, great to be in my alma mater, and I thank Professor Chobisa for inviting me to give this talk. So we all know that last year the Physics Nobel Prize went
Professor
to,
Dasgupta, you may want
yeah,
to click on this hide so that it does not hide any. This stop sharing and hide. So click on the hide so that the bottom part is not.
okay,
Uh,
okay,
yes,
okay,
yes.
okay.
Yeah, thanks.
Is it all right now?
Yes, perfect.
Very good, yeah. Last year, the Nobel Prize in Physics went to three outstanding physicists. Half of the prize was shared by Professor Roger Penrose, who, along with Stephen Hawking, had proved powerful theorems that showed that in any gravitational collapse of standard matter, a singularity which is sheathed by an event horizon is an inevitability. So thereby they prove that general relativity generically leads to formation of black holes, while the other half was shared by Professor Genzel and Professor Andrea Ghez, who independently did painstaking observations of stellar motions around the center of our Milky Way galaxy. And from their observations, it was clear that at the center of our Milky Way, there is a supermassive object that is very, very compact, and theoretical considerations, therefore, imply that this compact object must be a supermassive black hole. The theoretical work of Roger Penrose and Stephen Hawking, they essentially used one of the pioneering equations that was laid down by Professor Amol Kumar Rai Chaudhuri, who in 1955, using Einstein's general relativity, had come down to one very useful equation that is called the Rai-Chaudhuri equation, and that was used by Professor Roger Penrose and Professor Stephen Hawking to prove their singularity theorems. Of course, we know that way back in 1930s and 1931, Chandrasekhar's work had showed that black holes are not merely theoretical possibilities emerging from general relativity, but astrophysical considerations, in particular, the core of very massive stars. If the core's mass is more than 1.4 solar mass, they would essentially collapse into either a white dwarf, provided the core's mass is less than 1.4 solar mass, while if it is more than 1.4 solar mass but less than about 3 solar mass, they will collapse into neutron stars, while if the core's mass is bigger than 3 solar mass, then black hole formation is inevitable. So the physical possibility of black holes essentially emerged out of the research work of these four gentlemen. And Professor Genzel and Professor Andrea Ghez, they independently had monitored the motions of stars around the galactic center. This is that Sagittarius A star, which is this point is towards our galactic center, and when the stellar motions were monitored roughly from 1995 to 2004 in real time, what was obvious is that there is a very compact but supermassive object at the center that causes the trajectories of the stars to go into either very eccentric elliptical orbit or circular orbit and so on. And to see how stellar motion can give evidence for the presence of a very compact object is, suppose one has a star going around in a circular orbit, then centripetal acceleration provided by the gravitational attraction of the central object would mean that v square by r is equal to gm by r square, and which would mean that v square is gm by r. Now, v square can be monitored by covering the motion of the stars over its full orbit, while r, the distance from the central object, can be estimated by looking at the angular separation from the center to the star and knowing the distance of the galactic center. This angular separation would automatically yield, by multiplying the angular separation to the distance, one will get the r. And therefore v square and r are measurable, and from that one can estimate the mass of the compact object. And here is a cartoon which shows that for the S2 is a star which had an eccentric orbit around the compact object, and its closest approach on 19th May 2018 was about 20 billion kilometers, and therefore the compact object size has to be less than 20 billion kilometers. And note that 20 billion kilometers in terms of AU, that is the astronomical unit, which is about 10 to the power 13 centimeter. So 1 kilometer is 10 to the power 5 centimeters. So 20 billion into 10 to the power 5, which is 20 into 10 to the power 14 centimeter. So it is just 100 times bigger than the distance between Sun and Earth. But the mass, which was estimated, is about 4.5 million solar mass. That means the compact object weighs 4.5 million times heavier than Sun. And from that, one can therefore immediately guess that this has to be a supermassive black hole weighing 4.5 into 10 to the power 6 times heavier than Sun, because no other astrophysical object with such large mass and size less than 20 billion kilometers can be stable. They, whatever configuration they begin with, they have to necessarily collapse into a black hole. And we know that Penrose and Hawking had proved powerful theorems in mid-1960s, essentially about the formation of singularity for such heavy object. We know now that all major galaxies that have been studied by astronomers, all galaxies so far whose interior dynamics have been studied, they exhibit supermassive black holes at the center of the galaxies. For example, this is a spiral galaxy which happens to give you, it poses its full face, that is, the disk is normal to the line of sight. Such galaxies are called spiral galaxies. Spiral galaxies are, of course, disk-shaped galaxies, because in such galaxies, stars and gaseous matter, they have high angular momentum, and therefore they are centrifugally supported in the form of disk. And the spiral patterns are those regions because of density wave emerging because of differential rotation are very dense along the spiral arms where very new stars are formed, and that's precisely the reason why the spiral arms, they outshine the regions between the spiral arms. Here is another example of a galaxy. This is an elliptical galaxy. This is a M87 galaxy, and this galaxy was in news because of the Event Horizon telescope, which essentially mapped the photon sphere region around the supermassive black hole, which lies at the center of this M87 elliptical galaxy. There are other kinds of galaxies too, like irregular galaxies like Large Magellanic Cloud or Small Magellanic Cloud. And similarly, there are mergers, and all such major galaxies show that at the center or near the center, there lies supermassive black holes. We also know that although black hole solutions are a fallout of general relativity, but way back in 18th century, Laplace and independently Michel, they had used Newtonian arguments to show that if a star's size goes below 2 gm, if the size go below 2 gm divided by c square, then even light can't escape from the surface of the star. The argument is simply the fact that one can calculate the escape speed from the surface of a spherical object of mass capital M and size r, and we know that it's a very trivial thing to obtain the escape speed, and escape speed is simply square root of 2 gm divided by r. And if you ask what is the size when the escape speed becomes speed of light, then one gets this radius 2 gm by c square, and if the size becomes less than this 2 gm by c square, then escape speed becomes even greater than c. So even from Newtonian physics, one can see that there's something funny that goes on when a star's size goes below 2 gm by c square. Of course, the first rigorous black hole solution came from Carl Schwarzschild's exact solution of the Einsteinian general relativistic metric around a spherically symmetric mass, and from that Schwarzschild argued that if the star's radius falls below 2 gm by c square, then your metric has a coordinate singularity at the Schwarzschild radius of 2 gm by c square. That means there is a mathematical surface of this radius such that any event that happens within this region, they cannot be observed by an external observer because light cannot cross the mathematical surface of this radius. Such a mathematical surface is called event horizon. And note that for a spherically symmetric object, we get the same 2 gm by c square, which Michel and Laplace independently had obtained. But that's not a surprising aspect, because after all, Newtonian gravity emerges as an approximate theory of gravity from Einstein's general relativity itself. So in other words, Schwarzschild's solution showed that if a spherically symmetric object, its size goes below 2gm by c square, then nothing can halt its collapse to a single point. That means the density becomes infinity. And if one calculates the geometrical radius of curvature, the radius of curvature becomes 0. In other words, the curvature tensor becomes infinity at this point. And we know that infinities are singular objects because physics breaks down. Why? Because all equations of physics are differential equations. So in order to solve differential equation, one has to give boundary condition, and infinities do not form proper boundary condition, and therefore you don't get physical solution when you're sitting at such singularities. So in other words, Schwarzschild solution itself indicated that black hole solutions are indeed there. Now this 2gm by c square, therefore, as a mark of respect, is called the Schwarzschild radius of a spherically symmetric black hole. In numerical terms, if one plugs in the value of capital G and small c, one can show that the Schwarzschild radius is 3 kilometers times mass of the black hole divided by mass of the sun. In other words, if you have a black hole which is 10 times heavier than sun's mass, then its event horizon radius will be 30 kilometers. While for the Milky Way black hole, which has a mass of 4.5 million solar mass, the Schwarzschild radius will be 3 times 4.5 million kilometers. All right. Right. So this is some mathematical detail. This is a Schwarzschild solution, and students who have not covered general relativity, they need not bother about this equation. I'm just, for the completeness sake, flashing this slide because this is the exact solution that Carl Schwarzschild had obtained. And you can see that the metric G00 and GRR, G00 is the time component of the metric, while G11 is the RR component of the metric. They become singular when R becomes 2gm by c square. And this was what was pointed out by Schwarzschild himself. In 1963, Roy Kerr, he obtained another exact solution for a rotating black hole. So rotating black hole obviously will not be spherically symmetric. It would be axially symmetric. And here, for the case of Kerr black hole, you of course have a mathematical surface which is spherical in nature, which is the event horizon. And for Kerr black hole, there is a region which is very interesting called the ergosphere. This light gray portion is the ergosphere, and the axis, this axis is a rotation axis. It so happens, well, this labeling is wrong. This is not outer event horizon. This is the outer surface of the ergosphere. This is not inner event horizon, but this is event horizon. So there is some labeling error. This is the event horizon, and this is the outer, this spheroidal surface is the outer surface of the ergosphere. The ergosphere has two peculiar properties. One is that if one comes from outside and enters the ergosphere, then once one is inside the ergosphere, one necessarily has to rotate with respect to distant stars, which are static, asymptotically static inertial frames of reference. So once one enters the ergosphere, one cannot stop. They must move with respect to distant stars. The other interesting property is that inside the ergosphere, there are negative energy trajectories. That means there are particle trajectories which rotate in the opposite direction to the rotation of the black hole, and there are trajectories which are counter rotating, for which the total energy is negative. Total energy means rest energy plus kinetic energy plus gravitational potential energy. Of course, the event horizon, once one enters the event horizon, one can't escape. Ergosphere doesn't have that problem. If one enters the ergosphere, one certainly can escape, provided one has positive energy. But if one has negative energy, one cannot escape out, because outside there are no trajectories which have negative energy. Therefore, if one gets a negative energy inside, that particle is forever trapped. This was, I will skip this part. I'll just mention that this was used by Penrose in a seminal paper in 1969, where he argued that if you have a positive energy particle coming inside the ergosphere and splitting into two particles, one particle gets negative energy trajectory, the other particle has, of course, positive energy. But then conservation of energy says that negative energy plus second particle's positive energy must be initial energy. So the positive energy particle inside the ergosphere must be having energy greater than the initial energy, and therefore one can extract the rotational energy of the black hole. Right, let us not deal with this anymore. Let's go into the puzzle of supermassive black hole. I'll skip these slides. Now, as I've already argued, that observations say that most galaxies that one sees in the universe, they have underlying supermassive galaxies at the core, and it turns out that there are more than 10 million galaxies that have been detected, out of which more than 70% are known to have supermassive black holes at the core. We of course know that today the universe is 14 billion years old. But when the galaxies were formed, then the universe was few billion years old, and there are quasars that are seen which have billion solar mass supermassive black holes at the core, and the quasar light that we see today was emitted when the universe was barely billion years old. That means the billion solar mass supermassive black hole at the heart of the quasars must have formed when the universe was less than billion years old. And that is the real puzzle of supermassive black hole. Let me skip all these. Yeah, so this is to just complete the supermassive black hole observation for our Milky Way galaxy. This is the Sagittarius A star, and the X-ray view has this kind of a image. These are the X-ray photon images, and right at the center there is a supermassive black hole weighing 4.5 million solar mass. And we also know that there are quasars. So, for example, the first quasar that was discovered by Martin Schmidt, it appeared like a star, and for a while people were confused whether it's a star or something else. But it could not be a star, because when the distance was measured and when the amount of energy it poured out every second was measured, then it was clear that it is pouring out energy more than a galaxy. So it can't be a single star. That's why they were initially called quasi-stellar objects. Quasi-stellar objects were shortened to the word quasar. And then there were, of course, quasars which emitted also in radio. Those were the radio quasars. And so this quasar 3C175, that means the 175th object in the third Cambridge catalogue. The quasar in optical looks like a star, but it is straddled by giant lobes, radio lobes, and there's a radio jet also. And initially it was a puzzle as to how quasars shine, although they are so physically so compact. What produces the energy of the order of 10 to the power 47 erg per second to 10 to the power 49 erg per second? What powers such high luminosities? And so here is another example of an elliptical galaxy, the core of which, from the core, you can see in radio, when you observe, you see the radio jets, radio lobes, and when you see the close-up, you can see that there's a bright point. This entire thing has a size of 17 arc seconds, and the bright core, of course, cannot be resolved. There lies a supermassive black hole whose mass is 500 million solar masses. Okay, and this is, of course, the M87 galaxy. This is the core of the M87 elliptical galaxy, and you can see a jet emerging. This jet, in the case of M87, it shines not only in radio but also in optical and X-rays. So the black hole mass, which has been estimated, is about 6.5 billion solar mass for the M87 galaxy. So the question is, how do such active galactic nuclei like quasars, blazars, radio galaxies, how do they pour out such gargantuan amount of energy per unit time? The model is that there is a black hole and there is a plasma that is going around with high angular velocity, and therefore the plasma is in the form of a disk. The accretion disk model was sort of given way back in late 1960s and early 1970s by astrophysicists like Salpeter, Lynden-Bell, and more fine sharpened by the models given by Martin Rees, Begelman, Blandford, and so on. So such active galactic nuclei, if one happens to be, if the line of sight is very close to the jet axis, then one sees a rapid variability in the emission. So such objects are called blazars. So active galactic nuclei, which are seen with line of sight going along the jet axis, almost close to the jet axis. One doesn't see rest of the galaxies. One sees essentially the emission formed by the jet, and one sees that the variability time scale is very short. And from that variability time scale, one can estimate the central, the size of the central engine which is causing the emission, because causality argument would say that if the variability time scale is t variable, then the size has to be speed of light into t variable, because the entire region must be causally connected in order that the variability is going on, the luminosity is changing by a factor of 2 or more. So the entire region must be participating, and special relativity says that the entire causal region has to be of size less than c into time t variable time, if t variable is the variability time scale. So in other words, if you have few hours of variability time scale, then from that one can see that C into T variable is of the order of 10 raised to the 14 centimeter. So in other words, if you have a 10 raised to 8 solar mass black hole, and if it happens to be a Schwarzschild black hole, then the event horizon radius is 3 into 10 to the 13 centimeter, which is less than 10 to the 14 centimeter. Of course, if your black hole is a Kerr black hole, then the event horizon size will be even smaller than the Schwarzschild radius. Right. So you see that in order to explain quasars and other active galactic nuclei, one necessarily invokes accretion of plasma around supermassive black holes. And therefore, and similarly, you might ask, what causes the jet formation? So the idea is that the differentially rotating plasma, because one can easily show from plasma physics that a plasma, highly conducting plasma, it carries magnetic field with it, and therefore, because the plasma which is moving closer to the black hole is moving faster than those portions of plasma which are further away, and because of the differential rotation of the plasma, the magnetic field lines which are carried by the plasma, there's something called flux conservation. So therefore, when the plasma density increases, the magnetic field also increases, and because of the differential rotation, the magnetic field lines get wrapped up into this helical shape, and therefore all the charged particles that are emitted from this hot accretion disk, they get collimated by this helical magnetic field by virtue of V by C cross B Lorentz force term. Charge times V cross B is a force acting, and therefore they cannot cross normal to the magnetic field lines to get collimated. And we also know that there are very powerful quasar. In this slide, there is this quasar J0100 plus 2802. It is one of the brightest quasars discovered so far, and you can see that it's the estimated supermassive black hole is 12 billion times heavier than Sun, and the redshift of this quasar is in excess of 6. That means the light that was emitted from this quasar to reach us today, the light must have been emitted when the universe age was less than billion years. All right. So therefore, one has to provide models as to how is it that when the universe was only 0.9 billion years old, how is it possible that you formed such a heavy black hole? So this is the central puzzle associated with supermassive black holes. There are other supermassive black holes also which has been seen. For example, a 40 billion solar mass black hole has been seen in a galaxy which is here. This galaxy is in the Abell 85, which is in the Abell cluster. Of course, this galaxy, which has a 40 billion solar mass black hole, it is relatively nearby. Its redshift is only 0.056. There are other issues concerning the supermassive black holes. It turns out that supermassive black holes observed in spiral galaxies and elliptical galaxies, they exhibit a tight correlation between the black hole mass and the mass of the central bulge. Okay, so even in a elliptical galaxy, there is a sudden rise of density of stars close to the center, and if one measures this mass of the central bulge, then for spiral galaxies, of course, the bulge is well defined. One finds out that there is a correlation between the mass of the central bulge and black hole mass. These need to be understood. So these are some of the conundrums associated with supermassive black hole. Here is another radio galaxy 0402 plus 379, and here you see that binary supermassive black hole of total mass 15 billion solar mass has been observed. These black holes are going around each other with a period of 24,000 years. Here is another merging black hole, a binary black hole system, and the orbital period is very large, it's 10 to the 5 years, and total mass of the black hole combined is 4 into 10 to the 7 solar mass. Recently, the Indian group, along with French astronomer led by Mousumi Das, it's a recent publication, they have found out merger of 3 supermassive black holes, all right? And they are fairly massive, about 10 to the 8 solar mass, then 10 to the 7 solar mass, and about 10 to the 7, 8 solar mass. So 10 to the 8 solar mass, more than 10 to the 8 solar mass, and 10 to the 7 solar mass. 3 black holes merging because of these 3 galaxies. So one of the galaxies earlier was overlooked because it is very close to the galaxy NGC 7733. And the new thing that was pointed out by this group was to resolve the 3rd galaxy, which is close to NGC 733. Right. And here is a very perplexing finding. One sees that there is a supermassive black hole here, and there are 6 galaxies from which matter is flowing. Of course, one can't find out whether it's flowing towards or outwards, but physics would indicate they will be flowing towards the central supermassive black hole, which weighs about billion solar mass, and something strange is happening, that matter is flowing in a filamentary manner. Well, I think I have already consumed quite a bit. I would now wrap up as to what are the various models that are put forward to explain how the black holes grow. So the central idea is that early in the around Z 15 to 20, there were population 3 stars, which were massive stars weighing more than 10 to the 5 solar mass, which because of the pair production instability, they quickly collapsed to give rise to about 100 solar mass relic black hole. And these 100 solar mass or 1000 solar mass relic black holes, they accrete matter by either swallowing matter, baryonic matter around them, or dark matter around them, and so on, and grow. But the question is, what is the time scale? And there are, so for example, dark matter evidence is already known to us from the rotation curve of stars in spiral galaxy, and also from the clusters of galaxy, which was way back pointed out by Zwicky in 1933, and later on for galaxies, Vera Rubin in early 1980s plotted the rotation curve, which indicated that further away from visible matter, there is dark matter halo. And so current model is that for the disk galaxies like spiral galaxies and so on, the visible galaxy extent is, so this is the disk of the spiral galaxy. These are the eccentrically moving globular clusters forming a spherical halo, but the dark matter halo goes up to more than 60 kiloparsec away, up to maybe 100 kiloparsec. And similarly, dark matter is also evidenced from the galaxy clusters containing more than 1,000 galaxies bound to each other, not only due to the standard mass, but also due to the dark matter. And so various models are there: Rees, Wegelman, voluntary, Priyambada Natarajan, and so on. Their idea is that if you have standard matter, and if they cool very fast, and if they are spherical, no rotation, then they can directly collapse. Similarly, if you have dark matter, then if they don't have rotation, they can directly collapse to form supermassive black hole. But their assumption that the matter, either, for example, in Rees, Wegelman, etc., their model, the baryonic matter have to cool very fast, and they should not rotate very much. So these are unnatural assumptions as to why should you have baryonic matter which don't rotate. You see, the problem with rotation is, if matter to begin with has a small rotation, when it is collapsing, because of conservation of angular momentum, they go into formation of a disk, and therefore because of centrifugal forces, they cannot anymore collapse. And therefore, to form black holes in these processes, you need to have spherical flow, either of baryonic matter or of dark matter. So the physics is very complicated, and those who would like to have a popular account, one can see the article by Priyambada Natarajan that appeared in Scientific American.
Patrick,
Yes.
yeah,
Yes.
there's some question by some student who
Okay,
wants to know
yeah,
what is
please.
baryonic matter.
Very good. Yeah. So all standard matter that we are made of, Earth is made of, our solar system is made of, they are called baryonic matter. Why? Because if you take a standard atom, then the atom's majority of the mass resides in the nucleus. The nucleus contains protons and neutrons have UDD quarks, and protons have UUD quarks. And as you know, quarks are the basic constituent which are called baryons. And any matter that are formed out of quarks are baryons, because quarks carry baryonic quantum number. And because normal matter like atoms, molecules, the major weight comes from their nucleus, they are called baryonic matter. Electrons are much lighter. So yes, neutral atoms and molecules, they have electrons too, but majority of the mass is due to the baryons. Is there any other question?
People, if you have any question, please feel free to
Absolutely. I mean, the whole idea
students,
is that you should ask any question that pops up in your mind. Don't be, it's not important that I bombard you with a lot of information. It is more important to be more analytical. That means it is more important that we think analytically. So please go ahead.
So Kahan, is that clear now, baryonic matter? Okay, thank you.
So please feel free to ask any question. As I tell all my students, all questions are equally important. There are no stupid questions.
So I had a question.
Yeah.
About when you're talking about Kerr black holes, you mentioned that within the ergosphere, the energy of the particles is negative, right?
Yeah. No, not all, but there are trajectories which correspond to angular momentum opposite to that of the angular momentum of the black hole. And there are trajectories for which energy is negative. Not all trajectories have negative energy.
So the question is, if you compare with in Newtonian mechanics, bound orbits will have negative energy, right?
Yeah, but such negative energy is only kinetic energy plus potential energy.
Yeah.
When we say negative energy, even you add rest mass energy.
Okay.
So that is possible only in the ergosphere or inside the event horizon. That means you're also adding the rest energy.
Okay. Fine. Thanks.
Are there any more questions? All right. So towards the last, I would rather have more time discussing and taking questions. All I will say is that we have an alternate model as to how to form supermassive black holes using dark matter. Our assumption is that the dark matter is made out of very light scalar or pseudoscalar particle. Okay, either like axions or, I had posited one idea of dynamical four form, which would also correspond to pseudoscalar. They can also be of very low mass. So very light scalar, pseudoscalar of mass of the order of 10 to the minus 20 electron volt or less, then if they constitute the dark matter halo of galaxies, then a fraction of this dark matter halo can undergo Bose-Einstein condensation, particularly if the pseudoscalar particles are moving with very low velocity, so that the de Broglie wavelength is much bigger than the typical separation between them. Then you can easily show that such very light scalars or pseudoscalars would undergo Bose-Einstein condensation, and we have used mean field approximation around t equals 0 and considered the Gross-Pitowsky equation with gravitational interaction, and we have shown in our work that you could produce supermassive black hole within 100 million years through the quantum evolution of the self-gravitating Bose-Einstein condensation. I don't want to go into the details using the Gross-Pitowsky equation, because if there are questions, I will talk about it. But all I will say is that one knows from previous research that any particle boson whose rest mass is less than 1 electron volt can undergo Bose-Einstein condensation at any temperature of the universe, because as the universe expands, the thermal de Broglie wavelength of such particles also increases, and similarly the separation between them also increases, but in such a way that the thermal de Broglie wavelength is always larger than the separation, and you can form a Bose-Einstein condensation. By the way, so this is just a cartoon to show that when does a typical collection of bosons, identical bosons, undergo Bose-Einstein condensate, which was essentially predicted by Bose and Einstein, but I was recently pointed out by Shrirup Rai Chaudhary that the actual work of Bose-Einstein condensation prediction was done by Einstein after, of course, Satyen Bose had shown the statistical mechanics of photons. Einstein generalized it to particles which have non-zero rest mass, so that there is a non-zero chemical potential, and he predicted the existence of Bose-Einstein condensation. And physics is very simple. As long as the particles are moving very fast randomly, the de Broglie wavelength will be much shorter than the typical separation, and therefore they will appear like a classical Maxwell-Boltzmann gas. But once the bosons cool so that the de Broglie wavelength become longer, and once the de Broglie wavelength become longer than the typical separation, then all the bosons, identical bosons, will go into a single state. That means such a system will act coherently, as though there's a macroscopic wave function. And we know the bizarre properties of superconductivity and superfluidity can be also explained by invoking such macroscopic wave function. Anyway, I think I will stop. It's more important that you bombard me with questions.
Okay, thank you, Professor Patrick. Now, if you want to ask any question, please raise your hands. Then I will pass the question to speaker.
Or you can just unmute yourself and ask.
Yeah, that is also possibility. Yes, Amrit Kumar.
Good evening, sir.
Good evening.
Sir, in one of the slides, you showed that as a positively energized particle enters the ergosphere of a rotating black hole, axially rotating black hole,
Yeah.
it breaks into two types of particle. One positively particle that has more energy than the previous particle, and one a particle with negative energy. So using that extra energy that has been splitted up, we can find out the rotational energy of the black hole, right?
No, not find the rotation energy. Are you able to see this slide of mine?
Yes, sir. Yes, sir.
Okay. So let me go to the present mode. Are you able to see the full slide?
Yes,
so
sir,
this
yes.
is the slide of exhibiting the Penrose process of extracting energy. So imagine that you have one test particle portrayed here with green color, which is coming from outside the ergosphere. So here one has plotted, one is viewing the Kerr black hole from its rotation axis, so that the ergosphere is here and the event horizon is here. So the green object comes in with positive energy and it splits into two objects. Let's put one as red, the other as blue. The red is in a positive energy trajectory, the blue is a negative energy trajectory, and therefore the total energy must be same as the initial energy. So therefore, if the blue has negative energy, then the red must have a positive energy larger than the initial positive energy of the green particle.
Yes.
So that will escape carrying higher energy, that means it will escape with higher speed, while the while blue fellow, because it has a negative angular momentum and it will spiral into the inside the event horizon, and it will decrease the angular momentum of the rotating black hole. So effectively, you have taken away the rotational energy of the Kerr black hole. So in principle, if you have a Kerr black hole around, you can use such a Kerr black hole to extract its rotational energy.
So the particle is extracting that rotational energy from that black hole. Am I just guessing?
Yeah. So the probe was the original green particle. The particle which has extra energy now, excess energy now, is the red particle.
Okay.
So you send in a particle with low speed and you get back high speed particle. So therefore, you have it appears like a engine that is giving you more energy compared to the initial energy that has been thrown in.
Okay. Thank you, sir. Thank you so much, sir. It was very
Most
nice to hear you again, sir.
Most welcome.
Thank you, sir.
Yes, any other question, query?
Don't feel inhibited. Be bold. Ask questions.
Yes, Kahan Vyas.
Good evening, sir.
Good evening.
Sir, I'm sorry this might seem a bit elementary, but I just wanted to understand from you that, like, how can we determine, like, when a star forms a different type of a giant, like a red giant or red supergiant. So, what is the criteria upon which we can determine that yes, this may lead to the formation of a black hole, or maybe a white dwarf, or maybe a neutron star?
Yeah, very good question. So, one has to study the stellar evolution mechanism. So Chandrasekhar, he first half of his career was devoted in stellar evolution, and today astrophysicists are fairly certain of their stellar evolution model for stars uh, whose masses are less than about 30 solar mass. Beyond 30 solar mass, there are some uncertainties regarding the exact model, particularly late stages of stellar evolution. But for 30 solar mass and less, the evolution of stars are well known. So initially, you begin with a protostar, a cloud which collapses, and as it is collapsing, its gravitational potential energy is becoming more and more negative. That means rest of the energy have to be converted. Initial kinetic energy gets because of turbulence, etc. They get converted to thermal energy, and when the core of such a contracting um, uh, gas cloud goes above about 10 to 7 degree Kelvin, then thermonuclear fusion, in which effectively four proton combine to form one nucleus, which is alpha particle, and releasing energetic photons and neutrinos. So all main sequence stars, to begin with, this is what happens. The core, their effectively four protons combine to form one helium nucleus, releasing a lot of energy. And because of that, the core becomes hot. The heat is radiated outwards due to many complex processes. The star itself becomes hot, and because of the heat, pressure builds up, and the gradient of the pressure, because of hydrostatic equilibrium, the star remains in a quasi hydrostatic equilibrium. But when the core becomes more or less all converted to helium nucleus, then helium and other proton, they combine to form carbon, then oxygen, nitrogen. There's a whole chain of thermonuclear fusion that goes on. And for stars which are like our sun, there'll be a time when the entire core becomes essentially carbon oxygen rich, and therefore now it will not be able to anymore undergo thermonuclear fusion, because the carbon and in order carbon, oxygen, nitrogen, etc. to undergo thermonuclear fusion, the temperature has to be much higher. For a sun-like star, it's not possible. But then something peculiar happens, because just above the core, there is still protons are there, hydrogen is there, and the shell around the core that undergoes proton, 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 proton. That means four proton nuclear reaction goes on. So the shell burns and of course produces helium, but a lot of energy is liberated, and because it is away from the core, and therefore the gravitational acceleration is lower, such an energy release will cause expansion of the envelope, and such a expanding envelope therefore leads to the formation of a red giant. So after about billion years, sun will become red giant. It'll expand. It'll swallow up Earth because the envelope expansion will go on up to Mars, and the Earth will get burnt up, and so on. But if you have a more massive star than sun, it can become a red supergiant. Even more massive star, it can become a blue giant. So depending on the mass and chemical composition of stars, various stages of evolution takes place. But for the formation of white dwarf, the core mass has to be less than 1.4 solar mass, the so-called Chandrasekhar critical limit. You will soon learn in your statistical mechanics that if you consider the Fermi-Dirac statistics of electrons, you can show that when the density becomes very large, you have to take into account the relativistic nature of Fermi-Dirac statistics, and that's what Chandrasekhar had done and showed that you cannot have a relativistic degenerate gas of electrons that can be in gravitational hydrostatic equilibrium if the total mass is greater than 1.4 solar mass. And if it is greater than 1.4 solar mass, necessarily it implodes. And when it implodes, then the density becomes very large. Electron will combine with proton to form neutrons. So essentially you'll get a neutron-rich star, which is called a neutron star. And if the, let me see whether I have any slide concerning that. But in any case, stars whose core mass is less than 3 solar mass, they can survive as neutron stars. But if more than 3 solar mass, then even neutron degeneracy pressure cannot halt the collapse of such a neutron-rich core, and it will become a black hole. So depending upon the core mass, various alternatives are there. Either you can have white dwarf, or you can have neutron star, or you can form black hole. I hope I have clarified your query.
Yes, sir. Thank you very much.
Most welcome.
Yes, Uday, please go ahead.
Yes, good evening, sir. I have a question. So we know that all mass is made up of protons and neutrons. And
Sorry, what? All
mass is mostly made up of protons and neutrons.
Except those which are dark matter or dark energy. So
Okay.
all standard matter that we have discovered in our laboratories, yes, they are made out of protons, neutrons, and electrons.
Okay, and we know that the density of a nucleus is fixed. And we also know that a nucleus does not undergo gravitational collapse to form a black hole on its own. So
That's because the size of the nucleus is few Fermi, and few Fermi is greater than the Schwarzschild radius. If you calculate the Schwarzschild radius of a neutron using neutron's mass or proton's mass, you'll find that the Schwarzschild radius is very, very tiny. The size of the size of proton or neutron is few Fermis. So therefore, they cannot collapse into black holes.
So is it possible to achieve densities that are greater than that of a nucleus? What I mean is it possible for protons and neutrons to arrange themselves in a way such that it is even denser than?
No, if you try to compress neutrons and protons, they will undergo a phase transition according to the quantum chromodynamic theory. These are called QCD phase transition. So if you take neutron-rich matter, for example, for a neutron star, the central pressure is very high, and theoretical models suggest that the central pressure is so high that the core of the neutron star, there is a QCD phase transition to quark gluon plasma. So in the tiny core at the center of the neutron star, you expect free quarks and gluons. Because as you know, in quantum chromodynamics, if you try to bring two quarks very close by, then the force actually goes down. While if you try to pull two quarks outwards, the force actually increases. So this is the strange thing about strong interaction. And so this is called asymptotic freedom. And okay, so if you try to compress neutron rich matter or proton rich matter to a great deal, so that from uncertainty principle, the average energy of such particles is greater than 150 million electron volt, then it will undergo quark gluon plasma phase transition.
Okay.
Okay, so because of the time constraints, we cannot go forward too much. So let us thank Professor Patrick for such a nice talk on the aspect of supermassive black holes. And Professor Patrick, we would be very happy to host you physically in BITS Pilani in near future. So if
Thank you very much, Professor Chobisa.
we would be very happy to invite you, and we would be happy to learn more things from you. And on behalf of the physics department, we are grateful that you accepted our invitation.
No, it is my pleasure. As always, I enjoy interacting with young people, and so the pleasure is all mine.
Okay, so we would be happy to see you in near future.
Sure.
Maybe through online if you are for a sabbatical leave or for 1 year. In that case, through online. Else, we would be happy to receive you or hear you offline in Pilani campus.
Sure. Thank you, Professor Chobisa.
So thanks to all of you who have attended this talk. And now we can disperse.
Thanks, Patrick. Thanks for the beautiful talk, and your pedagogy is always brilliant and bang on. It's really a
thank you,
pleasure
Rishikesh.
to hear you. I mean,
thank you, Rishikesh.
Make complex topics, come to us so beautifully and so simply. Couldn't have imagined black holes being taught so nicely.
No, you're being kind. You're being kind, Rishikesh.
No, I'm
My
being
best
honest.
wishes to you and family. Take care.
Yeah, Kaushal was here. She had to go. There was a call from home, so Kaushal was here.
Yeah.
Thank you.
Thanks, Patrick. Hope to see you sometime in Pilani. I mean,
definitely, Tapumai. Thanks. Definitely.
Okay. Good night.
Good night. Take care, everyone. Bye.
Thanks once again. Bye.